Okay, this is part 2 of my video of linear regression or intro to linear regression. So back in the first video, I made the 5 assumptions of what needs to be required for the simple linear regression. And what I want to do here is kind of look further and make it more clear on what these assumptions mean. Okay, so for our first assumption, which is linearity, it is pretty straightforward. So again, this is a linear example of what fits the criteria of our assumptions, and then this is a quadratic or cubic or, simply definitely not linear. We have as x increases, y, the change in y is definitely not constant. It's increasing even further as x increases consistently. So pretty straightforward assumption. Again, second assumption I kind of went over. I think this is not too difficult to interpret. We have our mean of the errors. If we add it all up, it must be 0. So we have errors on top of the fitted line and below, but because the errors can be negative, they have to equal to 0 when we add them all up. Homoscedasticity. So this is what I kind of didn't go over, and I said I will go over visually. So the first graph is a proper example of homoscedasticity because our data points, the differences between these data points and the fitted line, they are relatively constant. However, if we go to look at the second graph, as our x increases, the variance or the difference between these data points and then our fitted line, it's increasing as we go further down into the x-axis, because these data points are definitely relatively smaller compared to the ones further down. And obviously, it can kind of be the other way. It just has to be, for homoscedasticity, it has to be constant. And you might be asking, like, why? How do we know exactly if our data is homoscedastic? And the answer to that is visually we can sometimes see, but if we want to see like exactly, or we want to kind of give like a definitive answer, then we will have to test it, which is definitely later down the road. But the first way is always visually, and it'll be pretty obvious if the data is heteroscedastic. If it's homoscedastic, it's not always obvious, but if it's heteroscedastic, it's usually obvious. All right, fourth assumption, errors must be uncorrelated, or x and y's errors must be uncorrelated. So if we draw the residuals, which again are the differences of the data points and then the actual fitted line. So this horizontal line is just given by, it's only trying to find the difference between vertical differences of the predicted and the fitted value. And we draw a horizontal line because it's easier to see it that way. And so notice how the data is kind of like equally scattered around our line, horizontal line. And so if that's what we determine, then we can say that the x and y's errors are uncorrelated. In contrast to our line over here, where our errors might be relatively constant in terms of like the actual difference, but if we see the residuals, then we have the middle x values clearly being under the fitted line most consistently, and then the lower and then the very high values being over the fitted line. And so we can't have that because that like implies a trend within our errors. So our errors cannot have a trend. It has to be random. All right. So I'm gonna go over the topic of weighted properties for estimating the slope now. And so now, mathematically, to interpret all this is fairly difficult. I try my best to interpret how like these weighted properties can actually intuitively make sense, but even for myself, I cannot I couldn't really give like a very clear way to explain how like some of these mathematical formulas make sense. But conceptually, I'll try to make it as clear as possible. So if we recall that the beta 2 hat is given by covariance of x and y divided by the variance of x, we can kind of expand it to here, because variance of x equals sum of differences of x squared. So this is the same thing, and then covariance of x and y, this is also the same thing. There was like a join function of fx and y here, but we are going to or that's for continuous, so we're assuming this is discrete. Okay, so what our weighted variable does, wi, it'll only extract the x values, the differences of the x values. So when we're calculating b squared, we're giving in terms of the summation of w and y times y, the product of w and y. And so essentially what this w is trying to do is it's scaling the x values so that the quote unquote more reliable, or the x variables that are more reliable or not quote unquote not random are weighted more heavily. So the x variables that are right here, the ones that are closer to what we expect, are going to be weighted more heavily for beta 2. So again, like if we try to interpret this intuitively, like, oh well, the mean of x, the values that are closer to the mean of x will be weighted more heavily, so values that are more in the middle of the data will have a big greater impact to beta 2. In a way, I guess you could do that, but I think just generally we can kind of see that the W is really just trying to weigh values that are more reliable. So some interesting characteristics is that the sum of the weighted values will equal to 0, and then if we multiply by the x values, it'll equal to 1. I guess we could kind of think of this as like the error, expectation of error equaling to 0 for the first one, and then the probability of all the x's must equaling to 1, because x's in a way they're still count as a random variable, even though that might be confusing because we already know all the x values when we're looking into the data set, but they still count as random variables because they were still extracted from a unbiased, like a not unbiased sampling of the data. And so because of this, we can say that the beta 2 is given by the normal distribution of the weighted terms here. So kind of all of this, the characteristics and then the normal distribution, we can kind of just like relate it to what I went over in just like single variables of the random normal distribution or normal distribution, but we're calculating kind of more of like the trend, and then we're accounting for the weights of it. And then it's important to know that there's a difference between the beta 2 or the B2, which is our estimate, and then beta 2, which is our true parameter. So B2 is given by the beta 2, which is like the actual given like actual slope that we kind of theorize. We say theorize because it doesn't actually exist. We don't know what the true function is for our given data set, but we say that it's based off the true function plus the weighted errors. And so the W once again exists because we're accounting for we're scaling the errors so that we can make the errors that are more reliable or closer, the errors that are closer to the x values, or the errors that are more smaller or just minimal, we can scale those bigger. And so because the expectation of B2 equals the true parameter, even though, we're not going to get every estimator right on these type of graphs. Like, obviously, like it's unrealistic that the fitted line goes through every data point. We still call the B2 the estimator, which we will say it's unbiased. And then similar to B2, we have the B1, which is the intercept. It's kind of given by, again, the quote-unquote true parameter plus the randomness. And it will also say B1 is an unbiased estimator. Okay, and then, so that leads us to the following of what an unbiased estimator actually means. And what an unbiased parameter or estimator is focused on is it doesn't really account for the precision or the variance. Rather, it focuses on being unbiased. So visually, again, we can kind of see 4 examples here where the first, let's say it's kind of like when we're shooting, shooting bows and arrows, and then we're trying to aim for the middle. Let's say this is the example of a first target where we're consistently off, but it's around the same location. So then our bias would be large because we are nowhere near the aim, our center of the aim, but we have a small variance because they're located in the relatively the same location. For the second example, we have a small bias because they are definitely closer towards the middle, but we still have a large variance because they are scattered all over the place. And so the difference between each of these data points are a lot bigger than the first one. The next one, large bias, large variance. So we're nowhere near the aim, so that's a large bias. And then data points are scattered all around the mean. So that'll equate to a large variance. And then lastly, we have a small bias because we're trying to we have the data points very close to the middle, and then because they're all close together, we have a small variance as well. All right, and then mathematically, we can kind of see what not the actual coefficient, but the variance of what beta 2, beta 1, and the covariance of beta 1 and 2 equals. So notice how the standard error or the error of the variance and then the n are all given kind of the same thing for the first two parts of the formula, which means as the variance of the error increases, our data is made more inconsistent, and so our variance of the beta 2 and beta 1 will also increase. As our sample size increases, our data becomes more reliable, and so our variance of beta 1 and 2 will decrease. And then our variance of x, or let's do the mean first. As the mean increases, the variance of beta b1, was I saying beta the whole time? I really meant b1, but theoretically they're pretty similar. Anyway, the variance of b1 will increase as the mean increases, and then the covariance of b1 and b2 will decrease. And then I think I could say the hardest one to intuitively understand why it's happening is as the variance of x is increasing, the variance of beta 1 and 2 are actually decreasing. And so I'll demonstrate why here. So let's say we have the first graph shows a small variance of beta 1 and 2, or sorry, a small variance of x, because they're all condensed into like a small location, like we said here, right here, and here. And so if that's the case, we have a hard time estimating what b1 and 2, what the fitted line is, because we don't have an accurate representation of what the trend within our data set is. Opposed to if our data sets are more scattered through, we can kind of visualize or fit the trend way more. We have an easier time doing that. And so the analysis of this is that as beta 1 and beta 2 are, as the variance of x is in a bigger spread, beta 1 and beta 2 are then less likely going to be collinear, since the variable variance of x has increased. So if we, like for this graph right here, we don't know what beta 1 and beta 2 is. Like beta 1 and beta 2 will be very similar just because we can't outline a clear trend compared to this one. All right, so the variance of the error, not the variance of beta 1 and beta 2, but the variance of the error can be calculated as the sum of squared errors. We learned how to calculate that, divided by n minus 2. So essentially the sample size, except it's called the degrees of freedom because beta 1 and beta 2 are the variables we're accounting for. So pretty similar again, where think of like variance versus standard error. So like variance versus standard error, where for standard error we're dividing the variance by square root of n, versus the sum of squared error versus the variance of the error, where we're dividing by n minus 2. Or the degrees of freedom. It won't always be 2. We're just dividing by 2 because we have 2 variables. All right, finally, the Gauss-Markov theorem just says that under the 5 assumption model, just the 5 assumption model here, we have, if they are correct, if we are assuming that, then that means beta 1 and beta 2 have the smallest variance. Again, that makes sense because the variance is based off the sum of squared errors, and I went over multiple times how the sum of squared errors must be minimized for us to fit the data. And so if this is made true, then we call this the estimator. We say that the LS estimators, or the least square estimators of beta 1 and 2 are blue. An acronym for best linear unbiased estimators. So it must fit the 5 assumption model. It must be unbiased, as I demonstrated over here. And then it must have a smallest variance of errors, which again, that's how we calculate the fitted line. And then if those 3 assumptions are made true, then it is called blue, or the best linear unbiased estimator. And lastly, it's important to note that even though this is called the best linear unbiased estimator, the trend we make linearly won't always necessarily to be the best trend or the best fitted line we kind of estimate. It's only the best trend when they are under these assumptions. So they have to be linear and they have to be unbiased. So some of the trends we might make might not be linear and they might be biased. So, and then you might be asking, well, why, if it's biased and not linear, why would it be a better estimate? And that is a good question. So obviously, in the next video, I'll go over why some of the functional forms that are not linear. But I think just from what I learned in the future, I've rarely seen fitted functional forms that are actually biased. But nevertheless, just because we say that our estimates are blue, it does not necessarily mean that our estimates are the best possible form it can be, only if it's linear and unbiased, and if it's under these 5 assumptions. All right, that is going to be it. Again, in the next video, I'll go over the different functional forms that where x and y do not have a linear relationship,